technical. As you can see, now we have to go back and revisit all these ideas of gauge fixing and conformal anomaly in the presence of what we discovered today, the modular and the leftover parameterization symmetries. But let's talk a bit. How would we go ahead and compute tree-level amplitudes? So we're going to talk about tree-level amplitudes. So what we're going to do, so again, we're going to concentrate on a closed string case. So in this case, the scattering occurs on the roll sheet, which is the sphere. So the sphere is a manifold which I cannot cover with a single patch. Okay, so I need to introduce thinking of it as a manifold, I need to introduce several patches to cover it. And so, the way to do this, I can think of a sphere as two disks. So I cut out two disks, so one disk has a complex coordinate z, and so absolute value of z is less than rho. And then there is another disk, which absolute value of u is less than rho. So what I'm going to do, I'm going to assume that the radius of those disks is larger than 1, and so you can see that there is an overlap. And so I can construct a sphere by taking two disks and gluing them together. So right, so this is z equals to 0, and so my z disk is going to cover this part, right? So slightly below the equator, okay, and u equals 0, that's the other patch, right, on the sphere. So that's the center of my other disk, and there will be an overlap region somewhere about the equator of the sphere. Okay. Again, as usually when we think about manifolds, we introduce local patches, and that's what I did. I constructed a sphere by gluing local patches. But then there must be a transition. Function that tells us how do we go from one patch to another. So since we are dealing with roll sheets and we're doing computation in a conformal gauge, there must be a wild transformation. So there must be a wild transformation that would move us from one patch to another, right? To u. Okay, and so this u coordinate, right? We can identify coordinates in the following way. So u equals 1 over z. Okay, that in particular will correspond that those two disks will overlap. And so there will be an overlap region. Okay? So we're going to discuss metric in a conformal gauge, right? So the metric will take this form, e to the 2 omega, and then I have dz and dz bar. And again, to go from one patch to another, there should be a wild transformation, right? So we have to look, and the metric must be smooth, right? So So if we go, so this is a metric, how the metric would look like in the Z patch. So that is that bar. So I want, in principle, I can have an arbitrary Y factor here. And what we want to do, we want to get some idea what are the properties of this wave factor that would guarantee that we can go all the way from the north pole to the south, right? So dz, while keeping a smooth metric, right? So dz equals to minus 1 over u squared du. And so in this, so once I go to the u patch, then dz bar will become absolute value of z to the fourth du bar. And so what we need a transformation property on our Y factor so that it will cancel this Z factor, right? So as we go to the south pole, that will go to the south, on the south pole, u equals to 0, so so this is equivalent to Z going to infinity. And we want a smooth metric, so that tells us that omega must be proportional to minus 2 log absolute value of that. So so e to the 2 omega must decay fast enough so that it will cancel this z to the fourth factor. So if I ask the question, how do I write down a round metric, right? It's kind of the standard metric we write down on a sphere in terms of that coordinate. So a round metric on the sphere takes the following form. It's d squared, 4r squared dz bar. So here I have 1 plus squared. And actually, this metric looks, so you can see that in particular that this metric is well defined in a region as that absolute value of that is bounded, right, with through larger than 1. And once we go to the U patch, this actually transforms in a trivial way. This is du bar. Or 1 plus u bar squared. So in order to see that this is a standard metric, what you can do, you can just compute the, you compute, or see that this is actually a sphere. You can compute the Ricci scale and you will find out that this is 2 over r squared. So this guy, radius squared of the sphere. So recall, so I mentioned Riemann-Roch theorem, and I want to discuss this a little bit more in the context of a sphere. That recall. That when we have Euler character is positive, which is the case for a sphere, right? So for a sphere, Euler character is equal to 2. So in this case, the number of conformal Killing vectors is 3 times pi. So it's going to be equal to 6. But the number of moduli equals to 0. So in other words, all holomorphic metrics on the sphere, which is smooth, are equivalent to the round metric that we constructed there. Okay, up to holomorphic diffeomorphisms. Okay. So I told you that in particular, how do you compute the number of moduli, number of Killing vectors? It's given by Riemann-Roch theorem. And I'm not going to talk again. Joe discusses this in much more detail. So the only thing that I'm going to mention from this area, and that's what we're going to use to count these numbers infinitesimally, is the connections. The number of moduli. The number of moduli is equal to the number of holomorphic differentials. Number of holomorphic delta G ZZ. So what that means is that there is this tensor field with two holomorphic indices, and the number of moduli is how many independent rank 2 holomorphic fields I can introduce everywhere on the sphere. Okay, so that will the Riemann-Roch theorem tells us that that will correspond how many moduli I have, and the number of conformal killing vectors corresponds to number of holomorphic vectors. Number of holomorphic vectors, delta Z. Okay, again, the idea is given a manifold, right? So what we're doing, we're counting holomorphic tensors and we're counting holomorphic vectors. And the important point here is that once we define a holomorphic differential or a holomorphic vector, it must be well defined everywhere on the sphere. So we should be able to use a transition function to extend it from the north hemisphere to the south. Okay. So let's do this counting for a sphere so that we can kind of get a feeling what's being involved here. Okay, so let's suppose we have delta GZZ, and so this delta GZZ is holomorphic. Is a holomorphic differential near the North Pole. It is holomorphic. Near the North Pole. North Pole. Right? So small that. So what we need to do, we need to check under which condition this differential will be holomorphic near the South Pole. Right? So near the South Pole, it will transform into holomorphic differential in these U variables. And so we know exactly, because it's a tensor, right? It's a differential, so we know exactly how it's going to transform. So that's del U over del Z to the minus 2 delta GZZ. And so we know what the in the overlap region what's the relation between that and U. So that tells us that this derivative del U over del Z to the minus 2 is going to be equal Z to the 4th delta G Z. So now we ask a question from complex variables, right? So we have a function which is holomorphic in that variable, and it must be a holomorphic around infinity, right, as that goes to 0. So in particular, what this implies, so this delta G UU holomorphic near U equals to 0 implies that delta G ZZ is at least 1 over Z to the 4th. But that simply means that it's not holomorphic near. It can never be, unless it's identical to 0, it cannot be holomorphic near the origin. And this implies that that does not exist. GZF, which is simultaneously holomorphic around z equals to 0 and u equals to 0. Okay? Again, the idea is that the number of moduli corresponds to a number of independent differentials of this type. And we know exactly how those differentials will transform as we go from here down to here. And the condition that they are holomorphic must be that they should be expandable in a Taylor series expansion in terms of z and in terms of u. And the point is that if it is holomorphic here, it will not be holomorphic, right? And the other way around, if it is holomorphic here, it will not be holomorphic here. So, then according to Riemann-Roch theorem, what this tells us is the number of moduli equals 0. Okay, so the sphere, unlike torus, does not have invariant metrics. Okay. Now, let's look what's going on with holomorphic vector fields. Right? So if I have, again, so I have delta z, and I want to know what will happen with this. Suppose I have some holomorphic vector delta z around the North Pole. And I'm asking, how will it look like near the South Pole, right? So this is delta u, is a function of u. So it's going to be equal to, again, it's a vector field, so I know how it will transform. It's going to be del u over del z, delta z, and so this is equal to minus z to the minus 2 delta z. Okay, so the question is again, we want delta z to be holomorphic both about z equals to 0 and u equals to 0, which is the same as z equals infinity, right? And so you can see that the part. So if I think of this as a Taylor series expansion, how can I write down this holomorphic vector field? So I can have a complex number. It can be a constant, right? A naught. So if I have a constant is holomorphic around z equals to 0, and after I do the transformation, it will also be holomorphic around u equals to 0. And in fact, I can have two more terms, so I naught a1z plus e2 z squared. Right. So altogether, an arbitrary holomorphic vector, one which is holomorphic both near the North Pole and the South Pole of the sphere, can be parameterized at least infinitesimal level by 3 different complex parameters. Right? So 3 different complex parameters. And so that's where your number of 6 of conformal Killing vectors come from, right? So each of this is a complex number, so that gives you 6 parameter family. So immediately, what this tells you, that if I have a scattering of 3 strings, right? So I have to insert on the sphere 3 vertex operators, but I have a 6-dimensional leftover gauge invariance. So I can fix the position of the 3 vertex operators at any points I want on the sphere. And that will fix me this residual conformal killing group, right? And so it's only when I scatter more than 3 string states, then I have to integrate the vertex operators over a surface of the sphere. All right, guys? Good. So now, once we understood what the sphere looks like as a manifold, So we go ahead and we discuss computational correlation functions, right? So, scalar application. Okay. So before we were computing a path integral, right? We were computing vacuum amplitude. So I wrote the general expression how the path integral will look like if we have inclusion of the sources, but we never did any computation. So let's talk a little bit about it. So I'm going to introduce an arbitrary source, and I'm going to ask the question how my partition function depends on the source. So this will be a generating functional. So this will produce generating functional for the correlation functions, right? Because I can, as you will see in a second, that I can compute various correlation functions by simply taking functional derivatives of this generating functional. So what we have to compute, so again, I'm going to do it in the Euclidean set, in Minkowski setting. So I have I integrate d sigma, j of sigma, right? So what I'm not writing here, I'm not writing down the path integral, right, of so this means that there is a path integral. I have to integrate still with respect to all metrics, with respect to all x. Right. And I'm just concentrating on the source part. Okay? So what I need is dx, right? And so then I have e to the minus 1 over 4 pi alpha prime, and e to sigma. Okay? So, writing down. So in fact, actually, this is a source. This is a source term in Euclidean case. Okay. So Lx squared, and then I have plus I, and integral to sigma, g of sigma, x of sigma. Okay, so we're going to look at the, why am I saying that I'm not going to compute exactly exactly the Virasoro amplitude. So the Virasoro amplitude is kind of the scattering of physical string states. The point is that, notice what I did. So I left over the integral of DC system, right? And so that's what I'm not going to discuss. So I'm just going to talk a little bit how do we evaluate correlation functions, well, pretty much evaluating the functional integral with respect to dx. So there is a bunch of subtleties which is covered in great details in Joe's book. Again, I don't have time to go into that. So we will get some partial answer, and so in order to get the final physical result, what you have to do, you have to complete the path integral corresponding for the Gauss system. Okay, so how do we do that? So this path integral is very simple, right? At least on a sphere, because it's quadratic. So we're going to expand x mu in terms of normal modes on the sphere. Right. So what we're going to do, we're going to expand x mu of sigma as so we write down as the sum over all eigenfunction of Laplace operator on the sphere with some partitions, right? And then here, sorry, sigma, right? So those guys satisfy the Laplace equation. Sorry. Squared sine. Okay, and so the theorem guarantees that there is a Laplace operator on a compact manifold has a discrete set of eigenfunctions with a positive, once I include this minus sign, so with a positive eigenvalues. Okay, so all these eigenfunctions, they are orthogonal with respect to the metric here. Right? So this is a compact manifold here in our case. So d2 sigma is going to be g at psi prime equals to I prime. Okay. Okay, so now the point is that this expanded the set of eigenfunction x sub I provides a complete set in the case of square integrable functions, which means that whatever square integrable function x mu of sigma I have, I can always expand it in the series, and so I can do exactly the same. I can do exactly the same thing with the source term. Right? So we're just going to introduce j I mu. So I'm going to write it down as an integral d2 sigma j mu sigma x I sigma. Okay, so then my partition function will become simply a bunch of ordinary integrals, right? So it will be product I and mu, and then I have an integral over d. So now the integrals of a functional integral over arbitrary x mu will simply become an integral over these Fourier coefficients, right? So we'll have an infinite integral over an infinite ordinary integrals product of e to the minus omega I squared x I mu x I mu over 4 pi alpha prime, right? So what I did, I substituted the expansion into the Fourier convection, right? And I integrated by parts, and I used the equation for the eigenfunctions. Okay, so then there is one more term, I sine mu j I mu. Okay, so is it clear? You guys see how I will get this expression, right? So one slightly non-trivial step that I'm omitting here is this: you have to integrate the Fourier convection by parts, and so that will produce this operator. Okay. So good. So all these integrals are simple Gaussian integrals, except for the zero modes. Right. So all integrals are Gaussian. Except for the constant mode, right? So there will be the constant mode, which is an a constant eigenfunction corresponding to zero eigenvalue here. Okay. Again, I want to keep it normalized, right? So I want to normalize it with respect to the metric. So this guy is a constant, and it's given by an integral over d2 sigma square root of g to the minus 1/2. Okay. So we all know how to compute Gaussian integrals, and so we just go ahead and evaluate. And so what will we find out? That the generating functional will take the following form. So it's I, 2 pi to the d. So d, little d is, okay. The capital D, so this is a number, it's a number of fields on the wall sheet. D goes from 1 to 26, and then I have a d-dimensional delta function, right? Evaluated on J0. So the reason for that is that so all the integrals are Gaussian integrals, except for integral when it is x sub I is a zero mode. When it is zero mode, we don't have this term, and we just have e to the I, the Fourier coefficient of the zero mode times J0, right? And e to the integral of dx, e to the I kx, is just 2 pi delta function of k. So in our case, that will produce a d-dimensional delta function for the J0 component of the source. And all the other integrals are just Gaussian integrals, so I can evaluate it. So now I have a product with respect to all I except for zero mode. And then I will have here 4 pi squared alpha prime over omega I squared to the power d over 2. And finally, I have, again, so I'm not spending detail, I'm not talking. I'm not giving all details, I'm assuming you know. So this is, in order to evaluate this last piece, you have to complete the square, right? So once you complete the square, you will get this product. And then whatever is left from completing the square will end up being alpha prime I divided by omega I squared. Okay? Good. So now, in the last step, I'm just going to go back. I'm just going to go back to the field instead and rewrite this answer in terms of original source terms rather than the Fourier modes of the source. So that will be equal to I, 2 pi to the d, delta d of j naught. So here, what I have, so those are their product of all their eigenvalues of a Laplace operator on sphere, or in general on some compact manifold. So the thing here is not, okay, so here I'm actually doing the discussion in slightly more generality. So everything that I'm talking about here is valid for any compact manifold. So that's just a property of Laplace operator on a compact manifold. And so what I have here, I have a product of all eigen values except for zero eigen value, right? So that sign I is not equal to 0. And so that corresponds to a determinant of the operator minus number squared over 4 pi squared alpha prime. Okay? And I have to raise it. I have to raise it to the power minus d over 2. Okay? So, so these guys, once I go into their eigenfunction basis, so those are the guys that will give us minus omega I squared. And so this is just a rewriting of the product in terms of the determinant of the order. Okay, times. One thing is that this piece does not depend on the source term, right? So the only thing that depends on the source term is going to be this integral. And so I can now go back and substitute, right? So what are my Fourier coefficients of the source, right? So I'm going to substitute that expression there. And so what I will find out is it's e to the minus 1/2 an integral d2 sigma prime, and then I have j of sigma prime. And so here I have a reduced Green's function, right? J prime of sigma and sigma prime. Okay, so what do I mean by that reduced Green's function? So sigma 1, sigma 2. By the way, here sigma 1 is just an index, right? 1 and 2 are index. Each of these is 2 coordinates. Right? So this guy is equal to sum. Sum over I is not equal to 0. And then I have pi alpha prime divided by omega I squared, and then I have here x I sigma 1 and x I sigma 2. Right. So this is a very simple exercise. Again, I'm just taking the mode expansion, the coefficients of the expansion for the source term, substituted in this general expression. And then I have to integrate. I have to integrate with respect to actually, yeah. So. Yeah, I haven't performed any integrals at this stage, so I just simply substitute, and I'll get the double integral with this integral. Okay, so very good. So now we know that those are the eigenfunctions, right? So eigenfunctions. Of this Laplace operator on the sphere. And so I can write down the differential equation for my reduced Green's function, right? So this equation takes the following form: so g prime of sigma 1 and sigma 2. Okay, so minus 1. Prime. So this is Laplacian that acts on the first coordinate, sigma 1. And then I have g prime, sigma 1, sigma 2. So this guy equals to sum I is not equal to 0. And then I have xi sigma 1, right? And then I have xi sigma 2. So all I'm doing here is that I'm using the fact that those are eigenfunctions. So when I treat it with the Laplacian, I will get the same as I had before, times omega squared. So that guy will cancel, and I'll just have this sum. So if the sum will extend over the zero mode, because the set of eigenfunctions form a complete system, right? So that would mean that this infinite sum would be a delta function. Right? So this would be delta 2 of sigma 1 minus sigma 2, two-dimensional vector function divided by square root of g. But that would be the case if this summation would run over all possible i's, but it's not. So what I have to do, I have to substitute. I have to subtract. The 0. Okay, and actually, so you can see this is a differential equation that I have to solve on if you give me a compact manifold and we derived with you what would the path integral look like for an arbitrary source, and that path integral involves the reduced Green's function, and I would need to compute that reduced Green's function by solving this differential equation. Okay. So one property of this reduced Green's function, which follows from its definition, is that this Green's function must be orthogonal to x naught, right? Meaning that an integral square root of g x naught g prime of sigma 1 and sigma 2, so this integral d to sigma must be equal to 0, because all these eigenfunctions, they form an orthogonal set. And so this guy does not have a 0 mode. All right, guys, so I have 15 minutes. It's not very good. So again, these discussions were in all complete generality, but now we can go ahead and we can restrict to a sphere, right? So we can restrict to a sphere, and in this case we have, well, actually I'm going to restrict it on the sphere, and I'm going to write down the metric on the sphere in a conformal gauge. So ds2 squared e to the 2 omega dz bar. So one of the reasons that I keep wild vector is because eventually, if our series is wild invariant, the wild vector must drop out, right? And so that's one way. That's one way of keeping track that you actually don't have any conformal anomaly in your series, or figure out what are the conditions that conformal anomaly will vanish. Okay, so we have this this particular metric, and so the question is, how do I solve this this partial differential equation and find the reduced Green's function? And the answer is something that we already did, right? So we know that that if so I'm just gonna write down the answer, and we kind of all agree that yeah, that's a reasonable thing. So the first term, alpha prime over 2 log z1 minus z2 squared, right? So this term is the one that will produce a delta function, right? So remember that we started it a long time ago when we talked about conformal field series, right? So we solved for a piece of the reduced Green's function that corresponds to that. So the other terms must correspond to subtraction of the 0 mode, and so I can write them down as f of z1 bar plus f of z2 bar. So so what I am writing here, right? So I wrote the equation for the Green's function where I act with the Laplacian on the first coordinate, but I can write down in exactly the same equation where the Laplacian acts on the second coordinate. And so so what this tells me is that there must be a symmetry by changing 1 and 2 indices, and so that's why that whatever function comes up. So now I'm looking for a solution of the PDE so that this guy equals to minus x naught squared, right? So whatever the solution I find for Z1, I have to add exactly the same for the Z2, okay? And so in fact, we can write down immediately what this guy is, f of z bar. So the property of it is that if I act with Laplacian times alpha prime factor, it must give me minus x squared. And so actually, if you are careful a little bit, so now notice that what I'm doing, I have this wild factor, right? So if I have a wild factor, then the square root of g is going to be what? E to the 2 omega will contain e to the 2 omega. So x naught squared will come with e to the 2 omega. So I'm just going to write down the answer. And so x naught squared is a constant. And so here I have an integral e to z prime. So here e to the 2 omega z prime z bar prime, and then I have log z minus z bar prime squared, right? So now you can see what will happen. So if you act with the Laplacian on this f, your Laplacian will act on the z coordinate. So Laplacian acting on log will produce you a delta function. So I'm not writing down, I'm not keeping track. I'm getting worse and worse as we come to the end. Because, you know, I'm kind of getting to the saturation point in time. But stop me if it's not clear, okay? So, but I think, so you act with the Laplacian here on the log, you will get the delta function, right? So now this delta function will kill the integral and will pick up omega at the insertion, right? So which is exactly what would be here once you factor square root of g. X naught squared will be multiplied by e to the wild factor at the insertion point. So that's the right answer. Well, it's almost the right answer. The reason is that the reason why it's not completely right is because there is a zero mode here as well, right? So what is not fixed here is an arbitrary constant, right? Arbitrary constant. Actually, this constant is not arbitrary. So this constant is fixed by the condition that my reduced Green's function is orthogonal, is orthogonal to the x naught, right? So what I have to do, I have to substitute whatever this f I have with k. I have to substitute it in the reduced Green's function and integrate reduced Green's function over a sphere. And make sure that that integral will be 0, so that will tell me what this particular constant must be. All right, guys? Okay. Good. So what we did so far, we computed the Green's function. So now we can compute correlation functions, right? So we compute correlation functions by inserting vertex operators. So in particular, if we study S matrix elements, or if we study a scattering of tachyons, right? So scattering of tachyons. So then the amplitude for the scattering at the tree level of the sphere will be given by these expectation values, like e to the I k1 x inserted at sigma 1, e to the I kn. So I'm thinking that I have n tachyon insertions, x over sigma n, okay? And I need to evaluate this correlation function on the sphere, okay? Right, so we can immediately use the results that we derived earlier today. So the question is, what is the source term, right? So J of sigma, the source term is simply equals sum I equal 1 to n k sub I delta function of sigma minus sigma I. Right? So remember that we evaluate the general correlation function of the type I integral j of sigma x of sigma, right? And so if we choose a particular source of this type, which is the sum of ki times the delta function and the insertion of the vertex operator, then we end up computing precisely, this correlation function, which corresponds to a scattering of n tachyons on the sphere. All right? Okay, 7 minutes. So actually, in order for me to explain this in detail, it would be a couple of lectures, especially. Let's go 10. And okay. Again, my point here from now on is to give you an intuition that that's indeed what's happening, and you should be able to start reading Joe's book at that point. And next time I'm going to talk about toroidal compactification. But let me finish this. So so we know what we know exactly what the green function is, right? We know what our source is, and so so we can break down what is this amplitude. So this is when I have scattering of n tachyons, right, on a sphere. So this is going to be equal to I, and so here there is Joe denotes this number. This is just an overall constant factor. Right? Then I have a delta function. So remember that the delta function was a delta function of J0, right? And in order for me to get J0, I have to integrate J on the worldsheet with a constant eigenfunction. So what I'm going to pick, I'm going to pick up simply a sum of Ki. So here, before was delta D of J0. So now this becomes a conservation law, right, for case of I. And so, so what I'm having here, right? So this is a constant factor that comes from this determinant, x naught minus d, determinant prime of minus plus 4 pi squared alpha prime on the S2 minus d over 2. Okay. So this piece does not depend on p sub I. That's a constant. It can be evaluated for a sphere, right? And then there is a term coming. From. Right, so there is a. There's going to be a sum over ij, okay, and I is less than j. And here we have p sub I, p sub j. And here we have g prime of sigma I, sigma j. Okay. And then I have minus 1/2 sum over I equals 1 to n k sub I squared g prime of sigma I. Okay, so do I have it? Right. So remember that what we have here in exponential. So that was an integral of d sigma d2 sigma prime j of sigma prime, and then reduce Green's function. So in this particular case, the computation is very simple because all the source terms are just delta functions, and that's why I will be picking up the values of the Green's function at the insertion of my vertex operators case of I. Okay, so the last step, I'll just substitute what the Green the explicit expression for the Green's function, okay? And there is one thing that I wanted to mention, okay? So, I'm just going to write down the answer and we'll discuss it in some detail. So, the M is S2 equals 5, S2, D of Ki. And then I have e to the minus alpha prime over 2. So, right. So there is one subtlety that I didn't mention. So when we evaluate this integral, right? So when we evaluate this integral, there is a divergence, okay? And the divergence becomes at a coincident point, right? And so this particular sum is a sum evaluating for the same vertex operator. So what I have to do, I have to use here a regulated Green's function, right? So I have to regularize it so that the answer makes sense. And so at the end of the day, so the way we're going to regularize the Green's function by precisely as we go from a product of two operators to a normal ordered product of operators, conformal normal ordering. So we do that by subtracting, by introducing the subtractions, and the subtraction behaves like log of z minus log z1 minus z2. So this regulated Green's function, g regulated, is going to be equal simply. First of all, it's at the same. At the same point. So what I have. In order to get rid of the infinities, I have to subtract alpha prime over 2 log of the distance, invariant distance between the 2 points squared. And so this invariant distance will involve the Y factor, right? So there will be alpha prime times omega of sigma 1, sigma comma sigma, right? And then there will be this log, so plus. Okay, so there will be plus alpha prime over 2 log of z squared, and this would have to be cancelled with this log, and I will be left with 2 factors of f. So the regularized Green's function will simply be alpha prime times omega plus 2f z. Okay. So now, once you substitute the Green's function, the regularized one, you will find out that the f, in principle, there is a dependence on the 0 mode. So there is a dependence on this f. But the delta function in the momentum will tell you that the dependence on little f will drop out. And so, so the final answer for the scattering amplitude, something that I'm trying to finish writing, will be a sum of I ki squared omega of sigma I. Okay. So this term will come from the regularized Green function there. And then the first term here will produce me ij equals 1 to n. I is less than j. Absolute value that ij alpha prime ki kj. Okay, so so that's the final answer, and so this is a characteristic behavior. This is a characteristic behavior of the correlation functions. What you notice here is that there is an explicit dependence. There is an explicit dependence on the while factor, and so so this dependence will cancel precisely. So you can see that it cancels out precisely when our deckhands are on shell. Right, so when k sub I squared equals to 0, which is the on-shell condition for our vertex operators, there is no dependence on the while factor. So our scattering amplitude is while invariant. So you have to be a little bit more sophisticated so when you look for scattering of gravitons or some excited states, then the cancellation of this type will happen. You have to look at the while transformation coming from the square root of symmetric on the worldsheet. And it will always cancel out. It will always cancel out for on-shell states. Now, the last thing that I wanted to tell you, to mention, is that eventually, so we got the scattering amplitude, and it depends on where we insert our operators. So in order to get the final physical results, what we have to do, we have to integrate over the zi's. But here we have to be careful. We have to integrate only over those coordinates so some of the insertions we can fix by using conformal Killing symmetry, so in the case of a sphere, we can fix 3 positions, and so the scattering amplitude will look like a product not to n but n minus 3 of this type that ij, right? That's very schematically, and then what we have to do, we have to integrate over all possible insertions here, product of z sub I up to n minus 3, and so these physical amplitudes are what's known as Virasoro amplitudes in string theory, which will produce Virasoro amplitude. Okay, all right, guys. So we're going to stop here. So there is no lecture next week, and so the last class will be on April 17th. So sometime in between, please return your homework. And at the last lecture, we will talk about toroidal compactification. Okay, something that has closer relations to phenomenology. Right.